Have you ever wondered about the vastness of the universe and the extent of what we can observe? It's an intriguing thought, isn't it? When we talk about our universe, we're often referring to the observable universe, the portion we can see from all directions. However, this term may be a bit misleading. You see, while we can observe this part of the universe, we're not necessarily seeing it in real time. The observable universe stretches about 46.5 billion light years in radius. Now you might be thinking, wait, isn't the universe only around 13.7 billion years old? You'd be right, and here's where things get really interesting. This apparent paradox is resolved when we consider the constant expansion of the universe. So, while we call it the observable universe, a lot of what we're seeing is the universe as it used to be, not as it is now. Did you know the universe's expansion can create a sort of visual illusion? Now let's delve into that a bit. You see, the universe is a constantly expanding entity. This expansion can make celestial bodies appear as though they're moving away from each other at speeds faster than that of light. However, it's not that they're breaking any cosmic speed limits. This is a visual effect caused by the vast distances that light has to travel. Consider high redshift quasars. These cosmic lighthouses are currently moving away from us at what we perceive as superluminal speeds. But what we're seeing isn't their current state. We're seeing them as they were billions of years ago, when the universe was much younger and they were much closer. It's a fascinating concept, isn't it? The observable universe is not just a showcase of the cosmos, but a time capsule. In essence, the observable universe is like a window into the universe's past. But what about the future? Will we ever see beyond our current observable universe? In theory, our observable universe will expand over time. As the cosmos continues to grow, so too does our window of observation, inching further into the vast expanse of space. This means that, in the distant future, we might be able to glimpse galaxies that are currently beyond our reach, giving us new insights into the universe's past and present. However, there's a catch. As the universe expands, the galaxies emit light at longer and longer wavelengths. As their redshift increases, these galaxies will start to appear redder and fainter. Over time, they may disappear from our view entirely, swallowed up by the unfathomable vastness of space. So, while our observable universe may grow, it appears we'll continuously lose galaxies from view. It's a fascinating, ever-changing cosmic dance that we're privileged to observe. Imagine this. If our universe is indeed infinite, then somewhere out there, mathematically speaking, there must exist an identical parallel universe, an exact mirror of our own. This concept, known as the eternal inflation theory, suggests that the distance between you and your doppelganger in this parallel universe is a staggering 10 to the 29th power of 10. In simpler terms, this is a number so colossal, it's almost impossible for us to comprehend. It's like trying to visualize a trillion billion billions of zeros after 100 zeros. It's hard to visualize such a huge number, isn't it? That's because it's beyond human comprehension. So we've established the notion of infinite space, but what lies beyond our universe? Is there anything unimaginable? It's not a stretch to consider that our universe may be just a minuscule fragment of a larger entity, a region that has concluded its cosmic explosion. There could be countless more universes, each with their own set of laws, their own distributions of matter, and their own evolutions. Outside our observable universe, there could be places eerily similar to ours, yet so unimaginably distant that the light from their galaxies will never reach us. The universe is always expanding, always pushing the boundaries of what we can observe. And in that vast expanse, there are probably entities wondering about us, just as we wonder about them. Imagine, aliens in those places would also find us outside their observable universe. We are all in the same cosmic space, yet so infinitely far apart. Now let's talk about the universe being a structure much larger than the observable universe. Sounds intriguing, doesn't it? Imagine trying to grasp the vastness of the Earth while standing on a flat plane. Your view stretches as far as the eye can see, yet it captures only a tiny fraction of the Earth's total area. This is akin to our understanding of the universe. Our observable universe is just a small part of a much larger structure. Now think about the shape of the universe. Scientists measure the curvature of the universe, and findings currently hint at a near zero curvature. This suggests that if the universe is a closed sphere, then the observable universe is to the universe what the flat land under our feet is to the Earth. In this light, our universe, and potentially others, are just like that flat land, small parts of a much larger structure. We're merely tiny specks in the grand scheme of cosmic space. Let's take a moment to summarize our journey through the concept of parallel universes. We've delved deep into the notion that there could be a multitude of universes, each with its unique distribution of matter and subsequent evolution. This could determine the placement of galaxies, the planets orbiting stars, and even the development of life and civilizations. We've pondered the concept of infinite space and the mind-boggling expanse that lies beyond our own observable universe. We've also explored the larger structure of the universe, with our own being but a small part of a grander whole. According to the eternal explosion theory, our universe is only a fragment of a vast space, an area that has concluded its explosive phase, with similar regions accounting for countless more universes. Next time you look up at the stars, remember, somewhere out there, another you might be doing the exact same thing. When we look up at the night sky, we see a universe that is remarkably consistent and level. This is no accident. It's a fundamental characteristic of the cosmos that can't be explained by mere chance. The traditional Big Bang theory offers an intriguing solution to this enigma. It proposes that at the very beginning, the universe underwent an extremely exaggerated rapid expansion. Starting from a fraction of a second after its inception, in an unimaginably short span of time, the universe expanded by a factor of 10 to the 26th power. That's like an atom suddenly ballooning to the size of an entire galaxy. This dramatic expansion, followed by a slower, steady growth, gives us the uniform, flat universe we observe today. The Big Bang theory is not a theory about the birth of the universe, but a description of its evolution. Imagine the universe expanding from the size of an atom to the size of an entire galaxy in a fraction of a second. This is the picture painted by the theory of rapid expansion. According to this theory, during the first few moments of its existence, the universe underwent a phase of hyperaccelerated growth. In less time than it takes to blink an eye, it expanded by a factor of 10 to the 26th power. That's 10 billion times its original size. But this expansion didn't continue indefinitely. Just as quickly as it started, the rapid expansion slowed down. As it decelerated, the universe began to cool and settle. This allowed for the formation of elementary particles, atoms, and even background radiation. These are the building blocks that would eventually form everything we see in the universe today. In essence, the Big Bang was not the beginning, rather the end of the explosion. But what if the initial explosion never actually stopped? This is where the eternal explosion theory comes into play. According to this theory, our universe is merely a small fraction of an ever-expanding explosion region. In this grand scheme, there are always parts of the universe that are undergoing a dramatic expansion, an eternal explosion, if you will. Now let's picture this eternal explosion universe. Whenever a particular space ceases to explode, two other spaces continue the grand expansion. And when one of those two spaces settles down, it gives rise to yet another pair of spaces that carry on the explosion. This cyclical process, in essence, is endless. So, in the vast expanse of the cosmos, we find ourselves in a universe where the explosion has ceased, while simultaneously, other regions persist in their explosive expansion. The universe we know is just a small part of the whole, with some areas still exploding, and some areas where the explosion has stopped. Let's dive into the idea of parallel universes, specifically the second parallel universe. The concept of a parallel universe is rooted in the idea that our universe is not alone. It's part of an endlessly unfolding tapestry of universes, each unique yet connected. The second layer parallel universes are distinct from the first layer ones. While the first layer parallel universes exist within the same cosmic space as ours, the second layer universes dwell in realms where the explosive expansion has ceased. This is akin to a cosmic dance where every time a section of space halts its explosive dance, two other spaces continue the choreography, expanding and evolving. The second layer parallel universes are those dancers who have taken a pause, their explosive beginnings now a part of their past. They are parallel to our universe, yet they exist in a realm that stopped exploding, making them a fascinating world of their own. While the first layer parallel universes share the same cosmic space with us, the second layer parallel universes exist in spaces where the explosion has stopped, making them a world of their own. What if we told you there could be countless universes existing alongside our own, and the only thing stopping us from reaching them is the speed of light limit? This idea might sound like something out of a science fiction novel, but it's a concept that scientists have been pondering for decades. The existence of parallel universes and the speed of light limit. Two enigmas that might be more interconnected than we initially thought. To understand this connection, let's first delve into the concept of parallel universes. Think of them as separate realities, each one a different version of our universe, all potentially existing concurrently. Now imagine if we could visit these universes. The problem is there's a speed limit in our universe, the speed of light. No matter how advanced our technology becomes, we can't move faster than light. This speed limit might be the barrier that prevents us from reaching these parallel universes. But what if we could bypass this barrier? This is where the concepts of warp engines and wormholes come into play. These aren't just ideas from Star Trek or Interstellar. They're scientific hypotheses that suggest the possibility of compressing or folding space to travel faster than light. Warp engines, for example, propose the idea of bending space-time around a spacecraft, essentially allowing it to jump across vast distances in the blink of an eye. Wormholes, on the other hand, are theoretical passages through space-time, creating shortcuts between 2 points in the universe. Both of these concepts, although currently beyond our technological reach, present exciting possibilities for future interdimensional travel. However, these methods might not work if our destination is a second-level parallel universe. These are universes that, although existing within the same eternal explosion universe as ours, are fundamentally different, with distances between them considered to be infinite due to the explosion area. So, breaking the speed of light limit might open the door to parallel universes, but what happens if our destination is a second-level parallel universe? Let's delve deeper into the realm of second-level parallel universes, places that are similar yet infinitely different from our own. These mysterious realms, while sharing the same basic physical domain as ours, might have experienced different phase transitions. This could result in them having entirely distinct physical constants, such as varying proportions of dark energy, different intensities of the four fundamental forces, and even elementary particles with dissimilar masses from ours. These physical constants play a crucial role. They're not just responsible for the unique appearance of each sub-universe, but they also seal the fate of these cosmic islands. The tiniest fine-tuning of these constants could cause a universe to flip on its head. Imagine many of these sub-universes being unable to form stable space and matter due to variations in these system setups. Most of them might be eliminated simply because they're not up to the mark, unable to sustain the complex dance of cosmic forces. Now let's bring our attention back home. Our universe, with its specific set of parameters, has managed to give birth to all things and today's civilization. Everything is set just right, like the most harmonious symphony playing out on a cosmic scale. Is this a coincidence? A fortunate roll of the cosmic dice? Or could it be the deliberate orchestration of some unknown force? This question is beyond the reach of current scientific understanding, yet it continues to intrigue us. Parallel universes, whether first or second level, remain a tantalizing concept. They exist as entities, not as scientific theories, and the hallmark of scientific theories is their ability to be falsified. As of now, such a concept as a parallel universe cannot be tested in reality, but as a kind of rehearsal they allow us to test the inflation theory that proposed them. Parallel universes, whether first or second level, remain a tantalizing concept. Though they are beyond the scope of our current science, they continue to inspire curiosity and wonder. Perhaps someday we might find a way to test the inflation theory and bring these parallel universes from the realm of speculation into the realm of reality.